Thank you, Joachim, for the introduction. I hope I can give you some impression of the major milestones of the last 10 to 20 years, if not more. I have spent the larger part of my research life exploring the world of texture and or I would say the tree of texture. And in order to give you some structure, I always like this view that saying that the tree of texture in fact has three main branches, namely a branch about properties, because indeed crystallographic texture is very important for a wide variety of material properties. I've named here a few, but as we see there are more, and this continues to grow. Of course, the knowledge in this, as our use of materials becomes more and more intricate, more and more versatile. So also the demands on properties of materials becomes more complex, and also probably the role of texture in the control of these properties. Then there is a second branch on this tree, which is what I call science, because of course, speaking about crystallographic texture, it relates to crystallographic aspects of material science. And of course, crystallography plays a very important role in many different materials or metal phenomena, like I have named here a few of them: plasticity, recrystallization, grain growth. These are all what we call solid state transformations, and you cannot have a full comprehensive theory about these phenomena unless you understand the crystallographic features of these phenomena. And looking at the texture can give you some new insights in that context, as we will I will give you some examples of that. And then there is here on the left perhaps the newest branch on the tree, of which I will not speak today. That is that knowledge on crystallographic texture related features has given rise in these past decades to a number of new imaging techniques to visualize the microstructure of materials at different length scales, because crystallographic contrast is one of the most powerful imaging tools to visualize the microstructure from nano to macro length scale. And the texture community was very much involved, or a part of texture community was very much involved in developing these new imaging techniques. But I will not speak about this today. So I start with a few examples on illustrating you the importance of texture for material properties. Actually, I was thrown into texture life many years ago during my PhD, and I was studying, in fact, a typical texture property relation, which is exemplified here by this curve, which is for importance for electrical steels. You know that steel is primarily used for its mechanical functionality, but with one large exception. That is that as iron is also a ferromagnet, it can also be used for electromagnetic applications. And here on this graph, for example, you see on the vertical axis the magnetic induction with an applied field of 25 ampere per centimeter. That is a magnetic property. And on the horizontal axis, you see this A parameter. I will not go into detail, but it is a typical texture parameter. It's a parameter that you can directly extract from a texture measurement on the steel alloy. And you see that there is a very clear correspondence. So the lower the A parameter, the higher the magnetic induction, the higher the permeability. So for electrical steels, for example, until today, it is very the industry tries to control the texture so as to obtain steel sheets with lower and lower A parameters. This work was published already many years ago. Some years ago, I had Hadi Perghazi, my PhD student, expanded this work by not only looking at the texture, the crystallographic texture, but also looking at grain boundary positions, grain boundary inclinations, as they are called. And these grain boundary inclinations, if you want to determine them, you are bound to have to do a 3D texture measurements. Or a 3D orientation microscopy measurement. This is a lot of work, but Hadi has done this work, and I will show later more examples of this. And if you include also in the results the grain boundary inclination, that is that actually you have a much better, you can take into account the magnetic domains at these grain boundaries, or the presence of deviations of magnetic free poles at grain boundaries, virtual free poles, then in fact you can even improve the correspondence as compared to where I had led the work 20 years before, because we did not consider these grain boundary inclinations. As you can see in these data, the correspondence between measured and modeled properties are much better by adding more microstructural information. It's also a nice example, of course, that very often texture, of course, is linked with other microstructural other features of the microstructure. As texture is not independent. We will give more data of this later. Another very well-known example, perhaps the most well-known example, is the correspondence between Langford R value. This is the width to thickness strain in a tensile test, and the texture. So this is perhaps the most well-known texture-dependent large-scale used material properties, particularly because there is a very strong dependence on the deep drawability of a sheet material, be it steel or aluminium, and the R value. And you can see here, this is a graph which shows the average R value on the vertical axis, and which shows the R value on the vertical axis, and on the horizontal axis, the angle of the tensile axis with respect to the rolling direction. You can see then that the R value is typical, it's anisotropic, it depends on this angle, and it depends here, as you can see, on the rolling reduction. So if you have a 75% rolling reduction, you have what is called a fourfold anisotropy, or a four-year anisotropy, whereas if you increase the rolling reduction to 95, you have a total different profile, which is what we call a 6-year anisotropy. So these are, we can calculate these R values from models, and these are, and then you can do, for example, you can try to do some property optimization. This is the evolution, for example, of the average R value as a function of rolling reduction, the evolution of the minimum R value, and the evolution of the planar anisotropy. This is the difference of the maximum and the minimum R value. And you can see here that at least for this type of steel, for the textures produced by cold rolling and annealing in titanium alloyed interstitial free steel, you have an optimum cold rolling window of around 85%, what was used a lot at the time for this steel, which are typically used for car body panels in automotive applications. Of course, there is much more to say about this here. The red dots, they represent the experimental values. This is for not for steel, but it is for aluminium. You can see that aluminium has far lower R values, lower than 1. As you compare here the value of 3, where the average R value is way above 1, even goes to 2. That's why the steel alloys in general have a much better drawability, deep drawability than aluminium. What I wanted to illustrate here on this curve is that depending on the crystal, we use crystal plasticity models to model the R value. And the Taylor model is a very basic model, gives you, well, it more or less predicts the shape correctly, but not the actual values. Whereas if you want to improve on that, you need more advanced models, such as the ALAML model, which was developed by the KU Leuven group with Professor Van Houten, or the VPSC model, which is also a very well-known crystal plasticity model, which was developed by Carlos Tomé and Ricardo Lebenson. We are another aspect which probably is a little bit less known in the industry or in the application, is that it's not only a matter of using the appropriate model, that's important, but it's also a matter of using the right statistics. Here we compare different R value predictions, R value profiles, where we change the number of grains in the EBSD map from 2,700 grains to 24,300. And you can see that the improved statistics, the improved statistical representativity has a major effect on the accuracy of the R value prediction. Whereas I can tell you, I don't show you the textures. If you would look at the textures with your naked eye, you would not be able to see the difference. This work is, you could say, is this work finished? Did you seem to be happy with your results? No, it's far from finished, because we think that we still can have better quantitative predictions for more complicated materials. So this is, for example, for another type of steel. And here you can see different simulations. This is the result of ongoing work that we do in collaboration, TU Delft in collaboration with KU Leuven, where we try with crystal plasticity models, of course, to reproduce experimental data, but also we compare the so-called full field statistical models with the mean field statistical models with full field prediction, for example, obtained from a Damascus, like this was developed by Max Planck Institute in Düsseldorf. Okay, so I could say many more details about these curves, but unfortunately I don't have the time. It's not only R value or magnetic properties. Also, if you look at fracture, for example, this was a PhD of Nuria Sanchez. She defended her PhD some years ago in at Gent University, and she studied pipeline steels. This is a well-known X80 type steel, and here you have on the vertical axis is the Sharpie V-notch energy, and this is the angle of the long axis of the Sharpie notch sample with respect to the rolling direction. And you can see that there clearly is an anisotropy, especially at intermediate temperatures. For example, here at -40 degrees, you clearly see a reduction of toughness or an increase of brittleness. And we associated this with the particular texture of this material, namely because it is well known that for steel, the 100 planes are planes of brittle fracture. And the texture in this material was such that under an angle of 45 degrees, you maximize the area of 100 crystal planes parallel to the fracture plane. To and that's why under 45 degrees, you observe an increased material toughness. We even developed this one step further by looking at very much in detail with at damage initiation, in fact. So if you have fracture, it's the result of a process, and this process starts with small void nucleation, and we made so-called void maps on tensile test samples. This was for a dual phase steel. This was the PhD work of Behnam, Shakir Rifat, and actually he very much in detail looked at the local texture around here, around these voids, and that was the so-called void texture and the void ODF. And then we try to analyze these data. Actually, what we would like to have, but we don't have, is a damage model, a crystallographically resolved damage model. But as a kind of substitute for that, we used our crystal plasticity models, and we were looking, we combined these crystal plasticity models by a strain hardening model, which was developed by Jesus Galan Lopez, who also worked in our group. And then we scanned the, so if you have a crystallographic resolved strain hardening model, you can see which crystals exhibits specific stresses and strains. So the stress and the strain is dependent on the crystallographic orientation. And you would expect, I think it's a reasonable expectation, that there where you have extrema of stresses and strains at interfaces between different crystal orientations and different phases, that there you would these sites in the microstructure are most susceptible to fracture. So, and actually this is what we observe in this graphs. Actually, these graphs are overlays of, on the one hand, the void ODF, so the crystallographic orientations in the direct vicinity of voids, and on the other hand, the distribution of a specific component, epsilon 2,3, of the strain tensor. Right? So, and you can see in these graphs, wherever you have a maximum or a minimum of these strain components, you have a maximum on the void ODF. So this was a just a brief overview what you can do by studying the crystallographic texture and relating it with properties. Of course, if you want to, before you can measure the property of a material, you need to make a material. And we all know that the metal making process will affect the properties through the microstructure, and texture is an intricate part of the microstructure. So let's have a look now how we can what we can say about texture by the analyzing the manufacturing process. And I'm going to give here some examples for steel. And in steel, of course, we have a wonderful tool. That is the gamma to alpha phase transformation, which is very powerful solid state transformation to control the microstructure and also the texture. For example, this is a scheme of a typical hot rolling sequence finish rolling in steel, where you have 7 finish rolling passes, and you can see that all of the rolling passes here in this example are above the AR3 temperature, but a few passes are below the recrystallization stop temperature. So actually the material is in austenite condition, but below TNR temperature, you do not have a full interpass recrystallization of the austenite anymore. And you can see that in this case, it gives rise to a very particular texture, namely a rather strong texture, which is exceptional for recrystallization textures. So for transformation textures, with a strong maximum here on the 110, on the 112, 110 components. So hot rolling, a precise combination of hot rolling steps with respect to temperature is an important tool to control the texture of the steel products. Another example is that, and it's at some point we were doing annealing treatments on cold rolled steel, and it's an IF steel. We like IF steel because it's simple, in fact, because it's a single phase ferrite structure, and very often we use it as a kind of a model material. Because if we use it as a kind of a model material, because before you want to apply some a new model, or you want to check if you really understand something, if you don't understand it on an IF steel, the chance is very small that you will understand it on a more advanced structure, which has different phases. The particular feature that we were interested here is what is called texture memory. You can see here, this is a texture simply after cold rolling and annealing in the full ferrite phase, and it is a typical gamma fiber texture, like the ones that I've typical for IF deep drawing. Now, if you heat up this texture in the full austenite phase and you cool it down back to ferrites, we were surprised to see that the texture, in fact, did not change. It is as if the texture of the finished state somehow remembers the texture of the initial state. That's why we speak of a texture memory, whereas this was highly counterintuitive, because there are many good reasons to believe that that actually we expected a random texture. So I don't have time to go into the details, but with each transformation, in fact, the texture can weaken with a factor 12 or 24 folds. But actually, that's not what we saw. We saw a very strong texture. And in order to explain this texture, a mechanism was proposed, which was expanded upon in a paper by Professor Hutchinson. And it was based on what is called double Kurdyumov-Sachs orientation relationship. You know that if you have a parent austenite structure, gamma 1, the ferrites preferentially nucleates at the interface of two at an austenite grain boundary, as it is shown here. So because of a specific orientation relationship, you expect that the new ferrite nucleus will have a specific, what we call Kurdyumov-Sachs orientation relationship, just call it KS, with one of the neighboring grains. However, for a small minority of parent austenite grains, the two neighboring austenite grains is by coincidence such that this specific orientation relation can be fulfilled at either side of the boundary. In that case, we speak of a double KS orientation relationship. So this is not a general property of austenite grain boundaries. It is a property of only very special austenite grain boundaries. And this is, in fact, a variance selection mechanism by which, as Professor Hutchinson has shown, you can explain the texture memory mechanism. Because actually, this is in the forward ferrite austenite transformation, is if two austenite grains nucleate from the same ferrite, then these austenite grain boundary, if these are two austenite variants nucleating in the same ferrite grains, these two austenite variants, they have exactly such a specific orientation relation that allows for a double KS orientation, for a double KS correspondence. So here, during back transformation, the ferrite grain that nucleates at this special austenite boundary will be precisely the ferrite grain alpha 2 that existed on that location before, and that explains the texture memory effect. Now, it was not just a hypothetical model. We, in the PhD thesis of Hiske Land here, she proved on another system, iron cobalt. Iron cobalt is an interesting model system because there the transformation temperatures are much lower and you can have a semi-transformed structure even at room temperature. And with EBSD, she looked very carefully at early ferrite nuclei that we can observe for this system at room temperature. And it was indeed confirmed, our assumption was confirmed, that the large majority of these nuclei have a double Kurdyumov-Sachs orientation relation. That is a Kurdyumov-Sachs orientation relation at either side of the grain boundary. And this also was in another way corroborated, this assumption, by a paper by Erik Offerman in 20 years ago, but where it was observed that the actual activation energy was an order of magnitude, two orders of magnitude smaller than predicted by conventional nucleation theory. And we believe that this has to do with the double KS orientation relationship, because if you have a specific orientation relationship, you will have a coherent boundary. So if the austenite's parent grain has a special orientation relation, then the new nucleus can be surrounded all the way around with special grain boundaries, and therefore with coherent grain boundaries, and therefore it reduces the activation energy as it was observed from synchrotron radiation experiment and published in by Erik and co-authors. Of course, the other peculiar feature, because there is a kind of genetic orientation relation between parent and product orientation, it also allows you to write to make an image reconstruction of the parent structure. So that was the work of Edgar Gomez and Hadi Pirghadi, who published it last year. And here you see, so we developed a reconstruction model. And in order to validate this model, we validated it on a iron-nickel alloy, because iron-nickel alloy transforms below room temperature. So this is the parent austenite structure, but at room temperature. If you then cool it down to liquid nitrogen, you quench it, and you heat it up again to room temperature, then you see that this austenite structure has fully transformed to martensite. So, and then we can do an on-site evaluation of the reconstruction model. So this is the reconstructed austenites, and this was the original austenite measured on the same sites, and you can see that it corresponds quite well, with one exception, that is that the model has a problem in identifying the twins, and this you can see in the correspondence plot. So this is the misfit between models and measured crystal orientations, and in general it's quite satisfactory, but of course here at around 60 degrees we have a misfit peak because we do not properly reproduce the twins in the parent structure. Okay, let's now I've talked about phase transformation. Let's now talk a little bit about plastic deformation, because of course plastic deformation will have a huge impact on the texture. This is the result of a near in situ it's just a moment. This is the result of a near in situ rolling deformation. So actually this was a sample which was embedded. There was a split sample, in fact, which was embedded in a larger sample, which was rolled various passes of 6% each, and in between the pass each pass, we dismounted the sample and we measured the EBSD surface. So this is not an animation. This is the real evolution of the microstructure, and you can see how the material plastically deformed and how the crystals rotate. So as predicted by crystal plasticity models. Actually, if you look, this was an aluminium alloy, and these are the, so actually what you saw were crystal, what you saw were the strain increase from 6% to 24% rolling reduction at room temperature. And these are the experimental textures that is observed. For aluminium, normally we use the 45, 65, and 52, 45, 65, and 90 degrees section. And this is the full constraint model. Now, the model is not perfect, far from, but nevertheless, it somehow is reasonable. It keeps the track, and the main features of the model of comparatively simple full constraint model are capable of predicting the overall texture simulation. But this gives you a nice illustration that texture is really a statistical property of the microstructure, because if you look at individual grains, they do not look individual crystal orientations. They may have a very different behavior. For example, you see here specific orientations which are way off with respect to the model. You also have other orientations that follow the model, or somehow that first follow the model and then break away. But whereas the crystal orientation itself, more or less with reasonable correspondence, satisfies or is predicted by the theory, this is not the case for individual grains in the microstructure. So that's one important conclusion we can draw from this. Don't confuse crystal orientation with grain. Grain is a different concept in the microstructure than a crystal orientation. Crystal orientation may be distributed over many different grains. And actually, if you look here at the image, you do not only see, you observe two important effects. Of course, the shape of the grain changes, the morphology, but that's not what we are talking here about. We are talking about the color. You see that the color of the grains changes, but not only the color changes, you see also that there is an the colors inside the grains, they change. There is a gradient of crystal orientations, and that's even more explicit shown here. This is an in situ tensile test on an iron 3% silicon, 17% elongated. And here you can clearly see how crystals really fragment. So this was not actually this is what we call an oligocrystal. There's a material with very large grains. So the entire section here is of the tensile test sample. And you can see that where originally the grains had a uniform color, so at the end of the text, even after 17% strain, which is not that much, you already have high angle grain boundaries forming. So we call this phenomenon crystal fragmentation. And today there is a lot of activity in the crystal plasticity community to model actually crystal fragmentation. And in fact, there are two types of approaches. You have like in so many texture models, you have an approach which is based on mean field behavior, and these are statistical models. So I have listed here 3 statistical models that are reported in literature. We have worked with the model of Professor Toth from Lorraine University in France. And for example, these are some tests that were done in the PhD of
Soroush Nagdi at the Gent University, and we did severe plastic deformation by high pressure torsion, where you have a shear strain of 10.4 in commercially pure aluminium. This is the experimental texture. You can see that the full constraint Taylor model is producing rather poorly. That's because the strain is so large. These models are not suited to reproduce such large strains, precisely because they cannot reproduce the fragmentation behavior. And this is the model of the fragmentation model of Todt and co-workers. And you see that although it's not perfect, but it definitely produces better results than the full constraint Taylor model. And the advantage of such a fragmentation model is that you also can reproduce the grain size distribution, because if you have crystal fragmentation, then of course the grain size will be affected. And here you can see some correspondence between experimental and modeled grain size distribution. This was from a publication by Soroush. And the other aspect is that I don't show it here, but it was you can read it in the paper. That is that actually it was shown that you have a small minority of grains that do not really fragment, that seem to survive the incredibly large amount of severe plastic deformation without fragmentation. And these grains, these were the stable components of the texture. So actually, in order to have fragmentation, you need crystal rotation. It seems logical, but it's kind of nice if you can, or it's comforting if you can prove it based on crystal plasticity principles. Another type of models, which is in fact the work of Caro Sedigiani in his PhD at TU Delft. He works with full field crystal plasticity finite element models, and this work is far too extended to present it here. And in this, but this approach, you do not consider the microstructure in a statistical representation, but you work with what is called a representative volume elements. And here I'm going to show you. Caro used the Damask model from the Düsseldorf Advanced Material Simulation Kit from Max Planck Institute. And the result that I will show is from an IF steel. Here are some details, parameters of the simulation. It was a 2D simulation, but the striking effect here is that, in fact, this is also for IF steel, that by here you can see the simulation, and here you can see the measured EBSD. And we don't do a one-to-one correspondence here, but you can obviously see that the full field simulation succeeds in reproducing some important features like the occurrence of shear bands and deformation bands that you observe in the measured microstructure. As I told in the beginning, a texture is in fact only one element of the microstructure. And in fact, you should integrate the texture. The ODF, the orientation distribution function, is a statistical description of the crystallographic orientation of the microstructure. You can blend this in, you can merge this with other microstructural elements, so as, for example, the grain size. And last year, we published a paper with Jesus Galan Lopez, and in which we considered the grain size distribution, orientation distribution, whereby we have a statistical distribution function consisting of two parts, on a grain size part and on a crystallographic part, whereby you can then represent for different types, for different grain size classes. These are all different grain size classes. You can represent the texture. So, and at the time being, we just developed the mathematical formalism, and it's the idea now that we use this
to get a better statistical description of the microstructure. Okay, so there is a lot. I have to speed up a little bit, I'm afraid. There's a lot to do about the occurrence of shear bands during plastic deformation. This was already very well known since long ago. There is a seminal paper by Ushioda and Hutchinson in '89, in which a very nice theory is explained for the occurrence of shear bands in 111-11-2 orientations. And in fact, it is well known that shear bands appear in grains with higher Taylor crystal orientations with higher Taylor factor. And the reason is it's energetically, because these grains have energetically advantage by concentrating the shear, spreading the plastic deformation over in a very small zone of the volume of the grain. And actually, if you look on a map, the grains with in orientation space, the grains of Taylor factor map, the grains with the highest Taylor factor are the grains of the so-called rotated Gauss orientation. So the paper of Ushioda and Hutchinson described the phenomena here on this components, which is the 112 components. Oh, let me go back to my laser pointer on this. Whereas we decided to look at these components. And in fact, if you apply the theory of Ushioda and Hutchinson for the shear bands in 111, 112, which will produce you in the end the Gauss components, in the PhD work of Tuan and Nguyen Minh, he proved that the same theory, if you applied it on rotated Gauss orientations, it would bring you the cube orientation. Now, cube orientation in steel, this is very rare, but it is of practical importance, particularly for electrical steels. And the cube orientation for electrical steel is like the kind of holy grail, but very difficult to obtain. So, based on the prediction by Tuan, we started analyzing in detail the shear bands in rotated Gauss grains. And indeed, if you look very closely, you find cube-oriented shear bands in rotated Gauss orientations, as shown here in this example, and which was published in 2020. Of course, the idea is not to leave it at that, because the cube orientations in shear band is nice for academic confirmation. But if you want to apply it for electrical steels, you need to recrystallize and hope that the shear bands orientations will recrystallize. Also, here this is another very nice proof of the presence of shear bands in rotated Gauss orientations. So, but as I say, the idea is to recrystallize this steel and then hoping that these cube orientations, they will consume the rest of the deformed matrix. So this brings us then to the final part of my talk, namely about recrystallization. And well, it's I have to summarize a rather complicated story. Actually, you have to do inclined rolling. You cannot just do normal rolling. Why not? Because if you do normal rolling, the rotated cube components, that's the rotated Gauss component, this component, which is the precursor of these cube grains, that's a very small minority component. But if you do inclined rolling, you can increase the volume fraction of rotated cube grains. And after recrystallization, you see that you can really obtain a macroscopic cube texture in iron, which has ideal properties for electrical steel application. So here, for example, we compare this inclined rolling with shear bands from rotated Gauss with a conventional rolling, and you can obviously see the difference. So in terms of A parameters, this will have a much lower A parameter and much better permeability. There is another issue about the rolling texture, recrystallization texture. That is that there is a very striking difference between cold rolling and warm rolling. Here you see two, it comes also from the PhD thesis from Tuan and Nguyen Minh. And here you have two rolled steel sheets. This is electrical steel also. One is rolled at 900 degrees, and this is iron silicon. So it stays ferrite to very high temperature, though it's 900 degrees, but it's still ferrites. And this is rolled at room temperature. The interesting thing to see is that, in fact, the rolling textures, they are very similar. There is not a lot of difference, maybe a little bit of difference, but this also can be due to statistical scatter. But if you look at the recrystallization texture, they are wildly different. You can see here that after annealing at 900 degrees C, this is the texture that comes from the cold rolled sheet, and this is the text that comes from the warm rolled sheet, rolled at 900, or hot rolled sheet at 900 degree C. You can see here that you have a what we call alpha theta fiber texture, which also is very interesting, by the way, for electrical application. The cube component is not so strong here, only 2.7 as compared to the one originating from the rotated gauze, but it's something that definitely needs to be looked at. From a theoretical point of view, it's of course interesting to know why such similar deformation textures have such very different recrystallization textures. And this problem was addressed in the PhD of Konstantina Traka, who used a full field model based on cellular automaton approach, in which she applied a local growth law on the deformed microstructure. So this is a deformed microstructure, a cold roll deformed microstructure, and you can see that she very neatly reproduces the gamma fiber texture, as you would expect after cold rolling in recrystallization of low carbon steel. With the same, she didn't change anything about the growth law. The only thing that has changed is the input structure. So this is the structure not after cold rolling, but after warm rolling. And now with the same recrystallization physics in the model, you can see that the result is totally different. So it means that although the texture of the cold rolled and the hot rolled sheet was very similar, it means that the underlying microstructure, or even the substructure, was very different, and therefore gave rise to a different recrystallization texture. And I want to end my talk with a little expansion on a problem that is already for years kind of intriguing me, and that's the problem of what we call the enigmatic recrystallization texture component. This is a texture component that often appears during rolling and annealing of steel sheet after recrystallization. And it is a component which is on this fiber. This is in fact a specific, it's not the alpha fiber. On a phi 245 degrees, it is a fiber which is a little bit shifted with regard to the alpha fiber. And in fact, it's most often the component here, the 311136 component. That's the component here. You can see, you can find this all over the literature. So it's not a rare component. As always, if we're looking for an unknown texture component, we try to find its origin in the deformed structure. And indeed, you can see, if you look very close, this was work of Patricia Gobernado, we can see here actually shear band features in the deformed grain, which indeed have the 311, the enigmatic component, let's call it like that, 311136. In terms of modeling, we did some attempts by Tuan, and in fact, we don't have a conclusive argument. Otherwise, I wouldn't call it the enigmatic component any longer. The strange feature is that you can have this texture components by assuming that if you roll, if this is the rolling direction, this is the transverse direction, that you have a 2-1 shear. This is a shear that is in the transverse direction on a shear plane perpendicular to the rolling direction. Now, it's hard to combine or to imagine such a rolling components, such a strain component, sorry, with the plane strain compression of rolling. But nevertheless, if you apply a full constraint Taylor model and you start with an alpha fiber, the typical alpha fiber of rolling, then you can see indeed that after some strain of this component to one shear, you end up with what is close to a this parallel alpha fiber and the 31136 components. Another, just to illustrate this in another project, which was run by Hadi Pirgazi and Harishandra Langevar, we also looked very much in detail at IF steel texture, even in 3D. So this is a surface of 10 by 10 millimeter and 1 millimeter thick, which was measured in 3D. Now, I show here this data because actually the good news, because such 3D measurements are very, very time consuming. And at least in that scale, wide field 3D measurements, the good news is that you do not always need it, because if you're just interested in texture, this is a 2D texture and this is a 3D texture, you hardly can see the difference. So so if you're only interested in texture, 3D measurement is not necessary, but unless you're interested in features for which you need the third dimension, so like, for example, the grain boundary inclination, then you need 3D experiments. Why I'm saying all this? Because I want to use these data to show you something peculiar. This is the texture which was determined with very high degree of precision. Many grains on a really almost macroscopic size volume in 3D. And we split this texture. Actually, we extracted from this only the orientations close to the gamma fiber. This is a typical IF steel deep drawing texture. If you now limit yourself to only the gamma fiber grains, that's what you get. But the peculiar thing is here. If you only extract from this material the grains which are at least 30 degrees away from the texture, so they do not appear in the macros, in the overall statistical distribution, you can see here that nevertheless in the backgrounds of the orientation distribution, you clearly have the 311136 components. So this brings to the conclusion that this component, it's very widespread in BCC low carbon steel. Even if it's not a majority component, it only surfaces under very specific conditions. But even when it is present in daily common deep drawing steels, and we now even have a serious indication that this component is responsible for some property aspects of the material. This brings me to my conclusion. So I have given you a kaleidoscopic overview of about 30 years of texture research at various places, mainly Delft and Gent. I think perhaps it was not necessary, but it was shown or it was confirmed that microstructures are intricately complicated. And in order to fight this complexity, the standard scientific methods is statistics, and quantitative texture analysis is par excellence, I would say, a statistical method which has proven its value in the crystallographic aspects, but which I hope can be extended to other features of the microstructure, like grain size, grain boundary inclination, or phase distribution, particle distribution, why not? And for texture specifically, I think that texture studies provides, on the one way, a major gateway to better understand complex metal science mechanisms that are at the underlying the solid state transformations, and that play a crucial role, on the one hand, in shaping the microstructure during metal processing, and on the other hand, for a better, more quantitative description of
property structural relations. So thank you for being with me, and I will be happy to address your questions. Thank you.